Deep space does not kill you only with cold or vacuum. It also hits you with invisible particles moving near light speed, and some of them can pass through your spacecraft, your body, and your DNA.
That is what makes deep space radiation so dangerous. It is not dramatic in the movie sense. It is worse because it is quiet, constant, and hard to stop. Leave Earth's magnetic protection and the rules change fast. The danger is no longer around you. It starts moving through you. In this tape, we will follow what that exposure actually means, not in theory, but as a chain of physical consequences, from the first particles crossing the hull to the long-term damage they leave behind. Because in deep space, the threat is not just dying out there, it is surviving the trip with your body already altered.
At first, nothing feels wrong. The cabin looks normal, the systems are running, your suit pressure is stable. The walls around you feel solid enough. That is the deception. Radiation in deep space does not need smoke, heat, or sound. It arrives as high-energy particles from two main sources. Galactic cosmic rays come from outside the solar system. Solar energetic particles come from the sun during violent eruptions. NASA and ESA both warn that beyond low Earth orbit, astronauts lose most of Earth's natural shielding from the atmosphere and magnetosphere. That protection matters more than most people realize. On Earth, the atmosphere absorbs a huge share of incoming radiation. The magnetic field also deflects many charged particles. But in deep space, those defenses are mostly gone. Now, the spacecraft becomes your main barrier, and that barrier has limits. NASA says shielding can help against solar particle events, but it only reduces galactic cosmic radiation by roughly 7 to 15%. That sounds backwards, but it is real. The most dangerous deep space particles are often the hardest to block. Galactic cosmic rays include protons, helium nuclei, and a small fraction of heavy ions such as iron. That heavy fraction is tiny, but biologically brutal. These particles can deposit dense tracts of damage through tissue, producing complex DNA injury that is harder for cells to repair.
The first danger is accumulation. You are not waiting for one dramatic hit. You are collecting exposure every day. During Curiosity's cruise to Mars, RAD measurements found an average galactic cosmic ray dose equivalent of about 1.8 millisieverts per day. That number helped confirm that a Mars mission can build up a large radiation burden before landing even begins. Then comes unpredictability. Galactic cosmic rays are the steady background threat. Solar particle events are different. They can surge. A major event can sharply raise exposure over a short period. NASA notes that such events can, in principle, push crews toward acute syndromes, though the probability of a very large event causing nausea and fatigue during mission conditions is considered low, around 1 in 1,000. That is the second deception. A low probability does not mean low danger. It means you may not get many warnings. And distance makes response harder. In low Earth orbit, crews still benefit from Earth's partial protection. In deep space, there is no magnetic shelter to retreat into. ESA notes that solar radiation storms become more challenging the farther you move from Earth's magnetosphere. The third danger is biological depth. This is not only about skin dose. These particles can reach deep tissue. They can affect bone marrow, blood-forming systems, the eye lens, blood vessels, the brain, and the heart. NASA and ESA both describe increased concerns for cancer, central nervous system effects, cataracts, and degenerative disease during long-duration missions beyond low Earth orbit. This is where deep space radiation becomes more dangerous than people expect. Most people imagine a simple burn, but the real problem is layered damage. A particle passes through tissue, It ionizes molecules. It breaks chemical bonds. It damages DNA directly or through reactive chemical cascades. One hit may be repairable. Thousands over time become a biological memory. Not all of it can be erased. Some cells die, some survive with errors, some divide later.
Now scale that up. A months-long mission keeps feeding that process. Particles hit, molecules split, DNA fractures, repair systems respond. Some repairs fail, mutations remain. Inflammation builds, vascular tissue changes, neural tissue takes hits that are still being studied. The body keeps functioning, but the damage ledger grows, and shielding is not a clean solution. Thicker walls help against some radiation, especially solar particles, but high-energy galactic cosmic rays can punch through material and even create secondary radiation when they collide with the spacecraft structure. That means your shelter can sometimes become part of the problem. NASA's human health material states clearly that current shielding is much more effective against solar particle events than against galactic cosmic radiation. This is also why deep space hardware is stressed so heavily. NASA's Artemis mission teams described the deep space radiation environment for Orion as far harsher than near-Earth conditions, forcing new approaches to radiation hardness assurance. One NASA summary described it as roughly 30 times worse for that hardware environment. For humans, the meaning is simple. Deep space radiation is dangerous because it combines three bad properties at once. It is penetrating, it is cumulative, and part of it cannot be shielded well with practical spacecraft mass. That is the trap. You do not need a catastrophic failure. You only need enough time.
So what happens in the end? Not always a dramatic collapse. Sometimes the consequence arrives later. Higher lifetime cancer risk, possible cardiovascular and degenerative disease, possible neurological effects that researchers still work to quantify, earlier cataracts, a body that made the mission but paid for it cell by cell. That is what makes the danger feel wrong. Humans are built to fear impact, flame, pressure loss, visible failure. Deep space radiation hides behind normality. No sound, no color, no warning light for every particle that gets through. Just physics crossing the hull faster than fear can react. Science you can hear, dread you can feel. And the darkest part is this: if the ship still works, if the crew still breathes, if the mission still continues, has the real damage already begun?
That is why deep space radiation is more dangerous than most people think. Not because it always kills quickly, because it keeps working when nothing seems wrong. And every kilometer away from Earth makes that silence more expensive. If you want the next tape, subscribe. The archive keeps growing.